I'm Michael, and I'm going to talk about the challenges we faced when dealing with obfuscated function clones in binaries by using machine learning. Now, there's various different names for it. Fish also had it in his keynote earlier. I'm just going to call it function clone detection now. The issue we have is when we have an unknown binary, or we have a binary and we don't know, we don't have any debug symbols, we don't know any of the function names in there, and we want to find out from the binary code what the name of the function is, which is useful because vendoring or static linking in open source is common. We have embedded firmware, and we also have malware that reuses code, where we could use clone detection for version tracking, for example, or making it easier for a manual analysis. But malware also uses obfuscation. Our contributions in this work are an end-to-end function clone detection framework called OFCI, where we only rely on open source tools and make use of somewhat recent natural language processing research. We try to introduce a method for preserving call graph information that we named call ID. And we perform an analysis of the issues we faced when dealing with obfuscated clone detection and how we dealt with virtualized function clone detection performance. Our contributions can be roughly categorized into 3 research questions, starting with the first one: can existing approaches be reduced in complexity? So this whole project started off as a project for my master's thesis, and I wanted to try and improve models for obfuscated functions on my local machine, because I didn't really have a lot of computing architecture available, and I always like running code on my local machine. And models in recent architectures that have been published are too large for me to run on my local machine. So the goal with this was mainly to maintain the same level of performance while reducing the complexity in such a way that I could actually train it. Secondly, I tried to add additional features to improve the detection results. In this case, this is the call graph preservation information. And for the third research question, I tried to take a look on how we could potentially use dynamic analysis to kind of try function clone detection, which is usually a static approach on virtualization obfuscation. We try to answer these questions with our framework called OFCI, short for Obfuscated Function Clone Identification. And the work was largely motivated that the full code was largely not available in recent work. Sometimes there's part of the feature extraction stuff missing. Sometimes there's part of the model missing. Sometimes there's random code parts missing. And I wanted to work around that and wanted to make sure that everything is open source and implemented available. So we implemented this as a GitHub plugin. For the language model at the core of the approach, we used LBERT because recent approaches use BERT-based architectures like BERT or Roberta for program analysis. And OFCI works by using LBERT directly on disassembly text. Another design goal of OFCI was to make sure to use as much of the stock implementations as possible so that you could later swap out the model without having to change too much. So we're just using most of the stock stuff from PyTorch and the Hugging Face transformers, and only modify as much as we absolutely need. In order to deal with virtualized code, we need some kind of dynamic analysis. And to this end, we used instruction traces created by a simple pin tool. This is the rough architecture overview of OFCI. We have the usual pre-training and fine-tuning split as we have in natural language processing models these days. And at every step, we have the disassembler, our GitHub plugin, which exports the data, pre-processes, performs some light pre-processing, and then performs the training steps. And in the inference steps, where we generate the function embedding, which is a vector that allows us to identify the functions amongst others, we can optionally switch between the disassembler or GitHub plugin, or additionally using our Intel pin tool for tracing. And then we perform the lookup. So the first step is the feature extraction. And with the feature extraction step, we wanted to keep as much of the disassembly text as possible and only modify what is absolutely necessary. In this case, what we need to modify is the numeric constants, because when we want to feed this into a language model, we have to tokenize it in some way. And different approaches deal with the numeric constants differently. We took the numeric constants and wrote it out in a little endian, and then just added the tokens byte by byte to the normalized disassembly. Another thing that is visible here is that Ghidra, where the disassembly comes from, correctly identifies a name for a function call. And when we see something like that, where we have the name for a function call, we perform a lookup into our database and see if we know the function. And if we know the function, we get the unique ID that is stored in the database alongside with the function. And then we add this ID also into the normalized disassembly. In this case, let's assume we didn't find a function, so we add just a 0 byte into the normalized disassembly. Afterwards, we use Albert because BERT-like architectures are used in recent work. And because I tried to get this to run on my local machine, I picked Albert because it uses clever tricks to reduce the number of trainable parameters, and it fit into the GPU RAM. We perform pre-training, where we train on basically a whole disassembly text of our dataset, but only use a subset, so the training actually finishes in somewhat reasonable amount of time. And we train using masked language modeling, where we have the network mask tokens and then guess them and then compare whether the result is correct. For the fine-tuning step, we sample the function pairs from the dataset. And if they share the same name, we assign them a similarity score of 1. And if they don't share the same name, we assign them a similarity score of -1. And then the final training objective for the fine-tuning is to make sure that the cosine similarity of the embeddings goes towards the label, that is 1 or -1. Because we want to deal with virtualization obfuscation, static analysis, as we usually would do with the function clone detection, is not enough, because the code is compiled into bytecode and then executed by a small virtual machine. Now, if we only look at this code statically, we would just see the code of the virtual machine and not the code that actually runs. And even if we were able to find the bytecode, since we're using the textual representation of the disassembly, we can't just derive a textual representation of the bytecode easily. So our idea was to instead generate an execution trace of the function we want to compare, trace the instructions, and by tracing the instruction, hoping to implicitly capture the bytecode behavior that we would otherwise not see. And this is happening using ITLPin, where we write out every pin basic block that is visited, and then import this list into Ghidra and export the disassembly from there. For evaluating our approach, we use the dataset from recent work from T-Rex. This dataset contains real-world OLLVM obfuscated binaries and other unobfuscated binaries. It also contains binaries across multiple architectures, but we focused on x86-64. And because we didn't have any Tigris dataset available, we created a synthetic Tigris dataset for the virtualization obfuscation. We trained the model 1 week on an NVIDIA GTX Titan X for pre-training, which is roughly the same power as my local machine, just more stable than my local machine. And then the fine-tuning for 24 hours on my local machine with an RTX 2070. For the evaluation, we also look at 2 different tasks. For one, we have the function similarity, which we evaluate with the receiver operating characteristic. And for the clone search, we used precision at 1, which says basically the ratio of the correct functions that have been returned through the function clone search. First, we looked at the performance of a feature extraction process. Ghidra analysis is somewhat slow because usually a lot of analysis steps are performed that also involve the decompiler. I tried to toggle this to make sure that I absolutely only use the minimum set of analysis options. However, it turned out that without using the decompiler switch analysis, it would not return a full disassembly because it wouldn't even try to disassemble indirect jumps, even if this was contiguous in memory. So I wanted the memory, I wanted that analysis, but it's also the most expensive analysis. However, when we look besides the analysis, the parsing of OFCI is pretty fast. And when we compare this with the other tools that actually count for the parsing time, we see that OFCI outperforms TREX and SAFE in terms of exporting the function data. It's also worth noting that SAFE parsing performance here is kind of underreported because I use the reported values here, but I tried it, and for some reason, my local or the Radar 2 version would take a lot more time than is actually reported. So for our first research question, I took a look at the complexity reduction. In terms of model parameters, the largest state-of-the-art model at the time of writing was TREX, with 60 million parameters and 700 megabytes on disk. And because of using Albert, OFCI only requires 70% of space at worst, which is about 9 million parameters or 35 megabytes. So the parameter reduction comes from using Albert, but we also stripped away any additional features that TREX or SAFE used. So TREX had micro traces and additional steps prior to the classification. And we stripped this all away, trying to make it as simple as possible. When we look at the function similarity performance across different categories of obfuscation, we see that the ROC AUC score is always above 0.95, which is okay. That's somewhat in the range that we were expecting. And also, when we look at the comparison with TREX on the obfuscated function pairs across different projects, we were not expecting to catch up to TREX, but we were also kind of expecting somewhat better values here. So we were kind of disappointed, but the values still are not too bad for receiver operating characteristic. Unfortunately, this doesn't really translate into the function search performance, where we only perform about roughly 1/3 of TREX and ASM2VEC at best. So this is obviously not good. So what's happening there? So we looked at the function search performance, and we first looked, okay, we reduced the model complexity, and we threw away the additional features that, for example, TREX used with microtraces and so on. But TREX also reported values for how its model performed without the microtraces, and it gave us reason to believe that is still should perform reasonably well. But then Albert should also perform on the same level as about Roberto or BERT when we compare it to natural language processing tasks. So we can't really blame put all of the blame on the reduction of the model complexity. And what we also realized was kind of the definition of similarity that we had somewhat of an issue with, because we stated that for the similarity, we have the dataset rely on function names, and we mark a function similar if the names are similar. But this obviously poses a problem when we have the same name and different semantics, or when we have the same semantics and a different name, because then that will basically teach the model something that is not correct. And we've actually found quite a lot of functions just by comparing the function hashes that had this different name was around 5% of the functions we had in our evaluation set. There's also dataset differences in the values reported because we use the dataset from TREX, but we only later realized that TREX doesn't use the whole dataset, but uses specific versions of the bin utils and core utils and so on. So we had additional versions in the datasets that TREX didn't use. or at least not for evaluation. We also realized something that we also realized when we ran into the length limit of the transformer, because all approaches that are based on the transformers have some kind of input limits. And the pervasive strategy we found is to just discard everything after the limit mostly. We tried to split the function into multiple fragments that would correspond to the maximum input length of the transformer, and then try to combine these multiple fragments. And then we analyzed how our model performed based on the number of fragments. And we can see that as soon as we have more than one fragment, we have a steep drop in performance when it comes to function similarity. And the performance continues to drop the more fragments we have. So for the case of functions that are longer than what the transformer can handle, some kind of different approach would be needed, because we can only increase the transformer input size to a certain length until it becomes too expensive, or it becomes very expensive already soon if you try to run it on a local machine. For the second research question, we took a look at how our call ID feature performed, or if it performed at all. And we checked, does it have an effect? Somewhat. We have a very slight effect in the ROC AOC curves. It's almost non-noticeable, but it's generally favorable across all ROC AOC measurements. Now, this effect is bigger the more calls a function has. But for a bigger effect, we would also need a model redesign that actually factors the call information into the information process better. We have a similar image when we look at the precision for the function function clone search, where we also have a slight improvement when using call ID compared to when not using call ID. For our third research question, when we take a look at the virtualization obfuscated code, we again had issues. We took a look at what was going on. We saw, okay, our classification performance is close to random, or is random basically when we look at the function search, where we got 0 for precision. Now it's slightly non-random if we account for function clones between virtualized code. That is, we have two versions of the same code virtualized 2 different times. Now this gives us some results, but still not really worth mentioning. And we also trained this with the rest, so the results here could also affect the bad performance in the other evaluations. Now, what are the issues with the virtualized code? And the issues we have is mostly with the data set. Because we made the synthetic data set, we had no real world functions. And the way we generated our synthetic data set, our functions are too simple or too random, in the sense that they are not unlike any of the actual real world code. And we can somewhat see this when we look at the receive operating characteristic on the unobfuscated code pieces. And here we see that between 0 and 01, when we try to do the function similarity, we get the random performance here already on 0 and 01, because the model can't learn from the completely random data set. And when we look at 02 and 03, function pairs between 02 and 03, we see that we have a perfect classifier because nothing changed there anymore, because the third optimization step didn't do anything. Additionally, we have the issue that the traces we used are heavily affected by the input size limitation, because the traces are by far the longest inputs we have in our data sets. So in order to actually make effective use of the traces, you would first have to kind of compress the traces down into something that is more in line with normal functions. So in conclusion, we introduced the OFCI framework. For efficient feature extraction, we rely on open source tools, and we try to introduce a reduced model size. We introduced call ID, which has somewhat of a slight effect, and is probably worth pursuing in future work. And we analyzed the issues we had with the obfuscated function clone detection, which runs into training data selection and our definition of similarity. And we analyzed the performance of function clone detection on virtualized function clones, where we realized that the tracing approach is not effective without modification.